Good evening, everyone, whether you are here in person at the SAO or whether you are attending via Zoom. Thanks so much for coming, and a special thanks, of course, to Jacques van Delft for giving the presentation tonight. Jacques actually hails from the Netherlands and immigrated to South Africa in 1980, and he pursued a career as an electrical technician. And he developed a passion for solar observation in 1982, and he has been studying dedicatedly sunspots, I guess, ever since, and the influence on our climate. From 1996 to 2008, Jacques served as the solar section director for ASA, and he resumed that position in 2023. So thanks so much, Jacques, for coming, and over to you.
Thank you very much, Christian, for this introduction. And good evening, everyone. As he said, my name is Jacques, and I'm going to do a presentation. Let me just go to the next slide. So it's about solar activities and the Earth connection. This is a picture that I took quite a while ago from the sun with a lot of sunspots. And that's actually the center and the starting point of my studies that I started since 1982. But before we can go to the sunspots, we need to know a little bit more about what the sun is and what it is doing. Now, first of all, if we look at this image, you can see that the sun actually has a core, and it has a convection zone, a radiation zone, and then you've got the photosphere. Now, this is the inside of the sun, and it was revealed during the 1970s by technology that they used, the helioseismology. They used sound waves, and the deflection of those sound waves actually revealed what you see now on this picture. Now, I'm just going to concentrate first on the inside. In the core, you've got huge explosions, a nuclear process which converts hydrogen into helium. And it's a huge amount every second. It's 6 × 10⁻11 kilograms per second. And this nuclear reaction is actually giving us the light and the heat that we experience here on Earth. Now, all those hydrogen and helium explosions will actually make a lot of electromagnetism and particles that are getting excited. And those particles actually going from the core through the radiative zone to the convection zone. Once it reaches the convection zone, it speeds up, and it speeds up to the surface of the sun. And the convection zone is actually just like water that is boiling in a pot. It's boiling to the surface, and all those particles, electromagnetically charged particles, are actually causing a lot of magnetism. Now, the sun also has a magnetic field, and the magnetic field is actually running along this line between the radiative zone and the convection zone, and that's called the tacho line. Now, what happens is that those magnetic lines are actually poking through the surface of the sun, and this will actually cause a darkening on the surface, and that's where we see the sunspots. Just some other information: the distance of the sun is about 150.5 million kilometers away from us, and you can fit 109 sizes of our Earth in the diameter, which is 1.4 kilometers a million, 1.4 million kilometers wide. The temperature in the core is approximately 50 million degrees Kelvin. And when we go to the surface, it becomes a little bit cooler. It becomes 6,000 degrees Kelvin. Okay, then you see the density, the mass, and the power output. And the age of the sun at this stage is about 4.6 billion years. We are about halfway its lifespan. So the sun is going to be for some time, you know, still with us, and the rest of our people that come after us. Now, I've got a video that shows you the working of the insight, so let's enjoy this video.
It is impossible to just look inside of the sun, as there is no such technology that can see through the hot, bright, opaque surface. But by using the application of physics and computer modelling, astronomers can predict the sun's intense internal conditions. To understand what is happening within the sun, it helps to imagine that it is divided into 6 layers, based on the physical characteristics of each layer. So let's explore these dynamic and complex regions and find out what's contained within this gigantic celestial fireball that we see rise and set every single day. At the heart of the sun is the core, an enormous nuclear reactor that is possibly 1,000 times the size of Earth. This is where nuclear fusion takes place, when hydrogen atoms violently collide and fuse to make helium under extreme pressures and temperatures. The energy produced here is what powers the sun, and is where all of the heat and light that we see and feel every single day is created. The extreme temperature at the sun's core can exceed 15 million degrees Celsius, or 27 million degrees Fahrenheit, and the energy that is released during just 1 second of solar fusion is said to be far greater than 1.8 billion nuclear bombs. The next layer is the radiative zone, a region where energy from the super hot core is carried outwards in the form of photons or light units. This layer is not as dense as the core, but is still dense enough that photons bounce around and collide with nearby gas molecules over and over again. According to NASA, a single photon can take more than 100,000 years to travel from the core to the outer border of this strange layer and into the next region, the convective zone. Within the convective zone, the temperature drops below 2 million degrees Celsius, or 3.6 million degrees Fahrenheit, and the density becomes low enough that photons are converted into heat and carried outwards by convection currents. These currents are rising columns of hot gas next to falling columns of cool gas, which produces a rolling motion much like what can be seen in a pot of boiling water. We have now made it to a layer that we can see from Earth, the lowest part of the sun's atmosphere, a region called the photosphere. The photosphere is sometimes described as the sun's surface. However, it is not a solid surface like on a rocky planet, but instead a 300-mile or 482-kilometer thick outer layer of hot, opaque plasma. From this region, most of the sun's energy that was created hundreds of thousands of years ago deep within its core can finally escape into space, and about 8 minutes later we can see part of it in the form of sunlight. The photosphere is considerably cooler than the sun's interior, but it is still a blazing 5,500 degrees Celsius, or 10,000 degrees Fahrenheit. It is within this bizarre layer that features such as sunspots and solar flares can take form, although they are the results of processes and disruptions that have occurred in other regions of the sun. Above the photosphere is the chromosphere, a 1,250 mile or 2,000 kilometer thick layer of thin solar atmosphere that is riddled with jets of hot gas resembling a flaming forest. These jets are called spicules and are fiery wisps of plasma that sometimes reach out for thousands of miles before collapsing and dissolving. One of the mysteries of the chromosphere is that it gets hotter the further away you go, unlike the internal layers that become hotter the deeper you go. The outermost layer of the Sun is called the corona, which is Latin for crown, and is a thin, wispy part of the solar atmosphere. It extends out for several million miles and can only be seen during a solar eclipse or with special X-ray images. Just like the chromosphere, the temperature of the corona also increases with altitude, reaching a scorching 2 million degrees Celsius or 3.6 million degrees Fahrenheit. Currently, the source of this extreme coronal heating is still a mystery, although it is thought that the Sun's immense magnetic field could be playing a big part. Compared to all the other stars in the Milky Way galaxy, the Sun is fairly ordinary, but it does have one possibly rare feature. An orbiting blue planet that is inhabited by intelligent, curious creatures that are willing to study their star and so begin to understand the mysteries of the universe.
Now that we know what's happening on the inside, now we can have a look at the first thing that we noticed on the Sun is the sunspots. The Sun has an 11-year cycle in which we've got a solar minimum and a solar maximum. When we've got a solar minimum, there are almost no sunspots visible for a long time. But when we go up to the solar maximum, we can see a lot of sunspots and a lot of single groups and sunspot groups with a lot of spots inside one group. Now, at the moment, we are actually almost at the maximum of solar cycle 25. And that's why we have a lot of solar activities going on the last 2 years, and it's going up to, I think, the beginning of next year. And those solar activities can even get more severe as that we had the last couple of years. Now, if you look at the left-hand side picture, you will see the Sun. You will see some small groups, you will see some single spots, and you will see a very large sunspot group over here. Now what I did is I actually enlarged that group. You will see that here on the right-hand picture. And if you look from one side to the other side, you can actually fit in 14 Earth sizes in that distance. And that's about 175,300 kilometers. Now, when such a sunspot group can become very active. Now, what are sunspots? As we look at the way the sunspots actually occur on the Sun, there's a lot of magnetic fields that are actually poking through the surface of the Sun and then go through the atmosphere and then going back inside the Sun. And you will see those magnetic lines actually on the left-hand side picture. Now, those nuclear processes are causing those strong magnetic forces. And as soon as you get the magnetic lines poking through, the upward flow of the plasma or the ionized gas gets restricted by those magnetic forces. And those areas, as you can see here, are cooling down. And it loses a part of its light intensity. So it becomes darker. And that's when the sunspot becomes visible. Now let's have a look at another video explaining this.
At Kitt Peak Observatory in Arizona, solar astronomer Matt Penn studies the solar surface to discover how photons of light get trapped.
There's a bunch of cirrus today, but hopefully we'll get some data.
Using the McNath-Pierce telescope, he focuses the sun's light to scan the photosphere in detail.
So what we've got are a few small sunspots on the disk of the sun. We've got two sunspots, two large ones. They're heading off to the edge of the sun, to the limb of the sun. But they're all accompanied by smaller sunspots, groups of smaller ones following them.
Sunspots mark areas where light is trapped.
So a sunspot forms a dark spot by removing energy from that part of the sun. It's blocking the convective flows that transport the heat and the light from inside the sun to space. And so what we see then is a cooler region that appears dark to us.
A powerful force stops our photon dead in its tracks, preventing its light and energy from leaving the sun's surface. That force is magnetism. Sunspots take shape where intense magnetism from deep inside the sun blasts up through the photosphere.
The magnetic fields are so strong that it actually stops the convective motion of hot inner material from flowing to the surface. So you actually get what looks like a cool spot on the surface of the sun.
They can be huge, the largest over 10 times the size of Earth.
When you got those large sunspot groups and those magnetic lines are actually going from one spot to another spot, they can become so energetic, the energy can become so high that it actually bursts into a solar flare. And a solar flare is a sudden and intense burst of energy and radiation emitted from the sun's surface. These events are caused by the release of magnetic energy stored in the sun's atmosphere. The sun's magnetic field lines can become twisted and distorted over time, leading up to the buildup of energy. When these magnetic field lines reconnect or reconfigure, it releases a tremendous amount of energy in the form of light or X-rays and energetic particles. Now imagine those magnetic lines being the filament in a light bulb. And as soon as you put power on that filament, it starts to glow. And that's more or less what is happening with the solar flare as well. It's not just, but it's the release of energy that actually runs along those lines, and then all of a sudden it starts to light. And that is when we talk about the solar flares that we see. Now here's another video that explains this process.
Huge loops of magnetic energy arc out over the sunspots. Twisted and unstable, desperate to spew their energy, they create a magnetic bomb primed to explode.
And so if one magnetic field with stored energy sees another magnetic field, those two look at each other and say, hey, if we connect, we can get rid of a lot of energy. They do so, they reconnect, pow!
It's a huge explosion, and we call it a solar flare. And this can be equivalent to millions of nuclear weapons exploding simultaneously.
Solar flares erupt outwards into space at up to 4.5 million miles an hour, releasing massive amounts of energy.
Okay, let's talk about the coronal mass ejection, because those are caused by those solar flares. A coronal mass ejection is a significant release of plasma or energetic energy and the magnetic field from the sun's corona, the outermost layer of the atmosphere. This event can have substantial and far-reaching effects on the solar system, including the potential to impact Earth and other planets. Now, those satellites that are actually watching the sun 24 hours, 7 days a week, are equipped with cameras to look at the sun. But they put actually a disk in front of the camera to block out the light of the sun. Now, those white circles that you see in the middle of the disk is actually the size of the sun as it is behind the disk. So if you look at the blue one, this is the size of the sun behind the disk. And when you get a coronal mass ejection, it's actually bombarding a certain amount of energy into the universe. And you can see this as the explosion that took place here. This is a very, very high energetic explosion. Now, I've got another video that can show you what a coronal mass ejection is. Feature that is also visible when you look at the sun as coronal holes. Now, coronal holes develop due to the interplay of the sun's magnetic field and its plasma. The sun's magnetic field is constantly changing and is generated by the motion of charged particles within the sun. At times, the magnetic field lines become stretched and twisted, leading to the formation of a coronal hole. So what actually is happening that those magnetic lines and magnetic fields are actually fighting each other. And when they fight each other, you know, it can that they pushed the atmosphere open, and that's what the coronal hole is actually formating. So coronal holes are associated with fast solar wind streams. Out of those coronal holes, the energy streams very easily into the universe, and it can cause also coronal mass ejections and reacts with our atmosphere. The stream of charged particles that are ejected from the sun's corona into space. These fast solar wind streams originate from coronal holes because the open magnetic field lines allow particles to escape more easily. Now, the coronal holes are often found near the sun's poles or in regions where solar activity such as sunspots and solar flares are less frequent. It's interesting to note that this time of the solar cycle, when we actually almost at the maximum, we've got so many sunspots and sunspot regions and solar flares activities that the coronal holes are actually non-existing at the moment. And as soon as we go to the lower part of the solar cycle, when those activities become less and lesser, we will actually see more and more coronal holes, which then actually also can react with the atmosphere, which I will explain later. Now, the Sun-Earth connection, what actually the title of my presentation is, has three main components. First of all, the solar wind. The sun continually releases a stream of charged particles, mainly electrons and protons, known as the solar wind. The solar wind extends throughout the solar system and interacts with the Earth's magnetosphere, influencing the planet's magnetic field and the formation of the magnetosphere. Then you've got the geomagnetic storms. Those activities, such as solar flares and coronal mass ejections, can produce intense bursts of solar wind and magnetic energy. When these disturbances reach Earth, they can cause geomagnetic storms, affecting the Earth's magnetosphere, leading to disruptions in satellite communication, power grids, and navigation systems. And that is those geomagnetic storms is one of the storms that we actually experienced 2 weeks ago when we saw the auroras. Now, the auroras, the third aspect of the Sun-Earth connection. The solar wind can also produce beautiful auroras, the northern and southern lights, and when it interacts with the Earth's upper atmosphere, charged particles from the sun collide with the atmospheric gases, creating colorful displays of light near the polar regions. Now, the strength of the geomagnetic storm actually determines how far from the polar regions towards the equator people can see those auroras. So the stronger the auroras, the further northwest or southwest towards the equator the auroras become visible. Now let's have a look how it works. When a solar wind enters our magnetic field, this is a video that will explain the process on how we'll see the auroras.
Our sun is constantly blasting huge amounts of hot plasma out into space. All those charged particles have a big effect on everything in their path. So what's protecting Earth from the solar wind and solar storms? Earth's thick atmosphere provides some defense, scattering and absorbing solar particles before they reach the surface. But our planet also has a secret weapon, a strong magnetic field it projects into space, mostly generated by molten iron alloys moving in Earth's outer core. The area of space where the magnetic field interacts with the solar wind is called Earth's magnetosphere. Its shape constantly changes as it's bombarded by solar particles. As positively charged protons and negatively charged electrons enter the magnetosphere, most of them are deflected around Earth, long before they reach the atmosphere. The magnetosphere really gets tested when big solar storms, carrying more plasma and traveling at higher speeds, are on a collision course with Earth. While most of the plasma is deflected, some of it gets trapped in the magnetosphere and funnels back toward Earth along field lines emanating from the poles. As charged particles from the sun collide with nitrogen and oxygen molecules in our atmosphere, they create the cosmic light shows known as auroras. The bigger the storm, the further from the poles auroras can be seen. Some storms are so big they interfere with satellites, cause planes to alter their routes, and can create other problems. The vast majority of the time, these inconveniences are pretty minor, but the next time the solar version of a perfect storm overwhelms Earth's magnetic shield, we might not be so lucky.
Okay, let's have a look at some of the auroras that become visible when those geomagnetic storms are actually coming towards our atmosphere. Let me just start this video. Enjoy the auroras. I hope you enjoyed those auroras. Now we actually seeing a slide. This is my projection of my study. I actually started with the solar activities, and now that we actually know what sunspots and the inside of the sun and the solar flares and the coronal holes and coronal mass ejection, solar winds, now that we know that, now we can actually go closer to the Earth. So let's buckle up and let's come down to Earth again. So we are actually arriving there at that part of my study. So let's have a look at what the effect is of those activities on our atmosphere. Now, as you've seen, those geomagnetic storms create stunning aurora displays at the polar regions and can impact our atmosphere and technology. Now, we know that satellites can be influenced by those auroras. Navigation systems can be negatively influenced. Even the travel industry needs to be very cautious when auroras take place, that they actually reroute their routes. Travel industry, for instance, electrical supply network can be interrupted. Communication systems are most of the time, when auroras take place, disrupted. It can have a negative effect on steel pipelines. If they are not protected, they can actually cause rust patches on steel pipelines. And even electronic equipment can be damaged if you are close, to those aurora areas. What is happening, that the auroras actually take place in what we call the thermosphere. Now, those auroras actually have a lot of heat inside, and that air expands, and then it can actually have an influence on spaceships and satellites, for instance. Let me just see what is happening here, because the mainstream scientists were actually not believing that there's a connection between sunspots and climate, to call it in a very short way. As we know now, sunspots actually can cause solar flares and coronal mass ejections. Goes through the universe, it hits our magnetosphere, and it causes the auroras. They didn't see the connection with that situation with climatic behavior. But let's have a look at the solar cycle from 1600 up to 2000. Now, if we look at the dry periods that South Africa, the droughts that we experienced in history, look at the drought in 1926 and 1933, 1945, 1952, 1976, 1985, 1995, and even with the minimum of the last solar cycle, around about 2016 to 2021, we had a dry season, and they all appear in the minimum of the solar cycle. Now, that is something that I actually, when I started looking at the sunspots, that's what I actually observed physically, that when there's a lot of sunspots, there's obviously a lot of activity. It influences the climate in South Africa in such a way that, especially in summertime, that you get an increase of rainfall figures. And when we are at the solar minimum, it doesn't rain that much. We've got a drought. And interestingly, what I've actually noticed a couple of months ago, I read an article about Sir William Herschel. Now, Sir William Herschel was also a scientist that was looking at sunspots, and he saw a correlation with climate, and he discovered that the price of wheat actually was influenced by the solar cycle. So in other words, if you've got if you are in the minimum solar cycle, he discovered that the price of wheat on the stock markets actually went up. because the scarcity of wheat actually increased the price, and vice versa. So William Herschel actually in middle 1700s until early 1800s discovered actually in the same way that I actually observed. He discovered the same connection between sunspots and climatic behavior. Now you will see here on the right hand side, you will see the solar cycle that we are at the moment. We are here, this was in last month, so it's quite recent. And you can see on the red line, that's a prediction. The solar maximum for solar cycle 25 should be reached end of the year, beginning of next year. And interestingly enough, that when you go downwards with the solar cycle, that's where the El Nino develops. So, and the El Nino is normally connected to dry periods. And again, you can see it's when when we got the downward trends of the solar cycle. Now, the link between the solar cycle and Earth climatic change is the auroras. And the collision between those electromagnetic charged solar wind and the molecules in our polar atmosphere generates millions of amperage of electrical current. And the air inside the auroras can actually reach a temperature of 2,500 degrees. And that has an indirect influence in the regions of the atmosphere below where the auroras take place. So the aurora borealis serves as a visible indicator of geomagnetic activity, which can indirectly, not directly, indirectly influence the polar vortex. I will explain later what the polar vortex is, as well as the jet stream, through processes such as atmospheric coupling and sudden stratospheric warming events. So the heating up and the energy of the auroras is actually having an influence on the polar vortex and the jet stream, which I will explain here. Now, the sequence of events that leads up to climatic change or climatic behavior is first you get the aurora, then you get an influence on the polar vortex, which in itself then gives an influence on the jet stream. And below the jet stream, because of the disturbance in the jet streams, it develops low pressure systems in the polar regions, as you can see on this map here. On the left hand side, this is how the jet stream looks like. Now, what I did in 2005, I actually took the geomagnetic activities and I compared that with the development of the low pressure systems. Now, this is what you see on this graph. If you look carefully at this blue line, this is the geomagnetic activities expressed in energies. And the red line is the development of the low pressure systems. And you can see there is some sort of a correlation between the two events. You will see this is a downward trend. You will see a lowering of the low pressure systems, and it goes up. You get a dip here and a peak there and over there as well. So if you go along these lines, you will see the correlation is there. So that tells me something. There is a connection between the aurora activity and climate. Now, there's something blocking my. Let me just have a look. Okay, anyway. This leads to changes in atmospheric circulation patterns, including those of the polar vortex. Now, the polar vortex is a region above the North Pole as well as the South Pole, which is a low pressure system, and it's a circulating cold air. Now, the energy deposition from the auroras propagate downwards, influencing the stratosphere and potentially affecting the strength and stability of the polar vortex. Energetic particles from the geomagnetic storm can deposit energy in the upper atmosphere, particularly in the mesosphere and thermosphere. Now, the mesosphere and the thermosphere are those layers of the atmosphere. This is more or less between the mesosphere and where the polar vortex actually is taking place at that height. Just want to see what can I do with this. Okay, it leads to the change in atmospheric circulation patterns, including those of the polar vortex. And the polar vortex is a large area of cold air that typically surrounds the north and south poles. Sometimes parts of this vortex can break off and move southwards or northwards, depending on which pole that you're looking from, bringing frigid temperatures to the regions that don't normally experience such cold. Now, underneath the jet stream, underneath the polar vortex, you will get the jet stream about 9 to 16 kilometers above the Earth. And the jet stream is a narrow, fast-flowing ribbon of air found high up in the atmosphere, typically in the troposphere. Now, the troposphere is this area where actually our climate and the climatic behavior takes place. It flows from west to east in a wavy pattern around the Earth, driven by temperature and pressure gradients. Now, when auroras take place, the polar vortex is strong. The polar vortex is a strong and well-defined, and it helps to confine the jet stream to a relative straight and narrow path, circulating the polar regions. This tends to keep cold air in the polar region and warms air further towards the equator. However, when the polar vortex weakens or becomes disrupted by the auroras, it can allow the jet stream to become more erratic and meandering. This can lead to the development of weather patterns such as persistent ridges and troughs in the jet stream, which can result in extreme weather events like prolonged cold spells, heat waves, storms, and heavy precipitation in various parts of the mid-latitudes. So what happens is, as soon as the polar vortex becomes disturbed, it disturbs the ribbon of the jet stream, and you will see it becomes very wavy, and in those pockets it will actually develop low pressure systems. And those low pressure systems are actually then reacting with our climate. Now, this is an interesting event that I've noticed during my studies. You've got certain regions. You've got the Antarctic region. This is the area where the auroras take place. Then you get a tropical zone. This is the equator. And you got a northern tropical zone and a southern tropical zone. Now, interesting to see is that when it's our summer time, the sun is actually moving south of the equator. And this cloud of bands actually moves then also. This is the tropical, humid air with clouds, moves south of the equator. Now, as soon as the sun goes back to the northern hemisphere, when it becomes summer in the northern hemisphere, you can see that this band of clouds also moves to the northern parts of the tropical zone. Now, our low pressure has an effect on those clouds, which I will show you with the next slide. You can actually see here that when a low pressure cell develops, and the clouds are actually on the southern parts of the equator, the centrifugal force is actually sucking in moisture air to the center of that low pressure cell. And this is what causes our summer rainfall over South Africa. Now, during the winter, when this cloud band is going to the northern region of the tropical zone, this low pressure cell cannot reach that humid air, and the only thing that we will get is moist from the oceans, which is cold, and this is where our winter rainfall is coming in the southern parts of the country, and that is when we get the winter time and cold air circulating. Now, if we look at those synoptic charts at the bottom, This is an energy that took place, that came and of an aurora that took place. We had a high increase of energy in our atmosphere at about 8 o'clock in the morning. Now, if we look at the synoptic chart of that same day, which this is a synoptic chart that was drawn up by the weather service at night, 12 hour at night, and there were only 2 or 3 low pressure systems with 2 frontal systems visible. Now at 8 o'clock we got a certain increase of protons in the atmosphere colliding with our atmosphere. And 12 o'clock, look at the increase of those low pressure cells in this area. And this causes that also the adjacent cold front frontal systems that moves then to the west. And that is then influencing our climate. And that is how it works. That's my presentation. I hope you enjoyed it. And thank you for your interest and time.